Okay, hello everybody. This video I'm gonna give a lecture on strain transformation. So this video is not gonna be problem solving. I was planning to give this lecture in today's class, but unfortunately I had to miss the class. So I thought of recording this video and uh, I'm gonna post this on Blackboard, and you guys will need to watch this before coming to class on next Tuesday. Uh, okay, so all right. So the topic I'm gonna talk about is about strain transformation. If you remember, for 3D state of stress, we had okay, if I draw it like this. We need to have 6 stress elements, right? So we have sigma x, and this one, if I call this x-axis, this one y-axis, this one z-axis. Then I had this one tau x, y. I'm sorry, x, z, because it's parallel to z. This one will be tau x, y, and then let me zoom in. All right, so I'm gonna have here again tau xy. I'm gonna have here tau xz. Here I'm gonna have sigma z. Here I'm gonna have a normal stress sigma y. And then I'm gonna have here sig tau zy, right? And I'm gonna have here again tau yz. This one is technically is tau yx. Okay, so this is tau y. This one is tau yx, but it's going to be equal to this one, right? So if you remember, we said that we have sigma x, sigma y, sigma z, and then tau xy, tau xz, and then tau yz. And from equilibrium, we know that this is equal to tau yx, also this is equal to tau zx, and this is tau zy. All right, so by knowing this 6 state of stress, 6 stress elements, we can, our state of stress is fully defined. So, similarly, we have, counterpart of these elements in 3D for a strain. So let me show you that for, so the state of a strain in 3D, I'm gonna have epsilon x, epsilon y, epsilon z, normal strains, and then I'm gonna have gamma xy, gamma xz, and then gamma yz. And similarly, these 3 elements are equal to gamma y. This one is equal to gamma yx. This one is equal to gamma zx, and this one is equal to gamma zy. All right. So by knowing 6 strains, 3 normal strain, and then 3 shear strains, our state of a strain is fully defined. All right. And similar to stresses, we can have plane strain condition. And under plane strain condition, what happens is, so under plane strain condition, you have epsilon z equal to 0. So on one axis, normal stress is 0, normal strain. And then the shear stresses related to shear strains on that axis, related to the axis are 0 too. So these two are 0. And in other words, gamma zx and gamma zy are 0 too, right? So this is plane strain condition. Under plane strain condition, we can use strain transformation equations like this one that I'm going to write for you to transform strains from one coordinate system, one orientation, to another orientation. All right, so let's say, so strain I'm sorry. Okay, so let's say I have for one coordinate, like if I have epsilon x in this direction, if I have epsilon, for epsilon y in this direction, and then and also I have gamma xy. And I'm interested in finding knowing this, I want to know what would be my strains along x prime direction and y prime direction. You see x prime and y prime are again perpendicular to each other, but x prime makes angle of theta with my original x axis. And I'm considering this theta to be positive in counterclockwise direction. So I want to know what is epsilon x prime and epsilon y prime, and also gamma x prime y prime. So knowing these guys and theta, I want to know what would be my strains for this new coordinate or new element. All right, just similar to what I always talk about, stresses. I have for this orientation your strains. Now this is moving. We want to know what our new strains are going to be. But right now I'm limiting myself to 2D. I'm into plane strain condition. All right, so the transformation equation for a strain is going to be like this. So epsilon normal strain in x prime direction is going to be equal to this. Very similar to what we had for stresses, with one small difference. The only difference you guys see here is that here, if you remember for a stress transformation, we had here tau xy sine of 2 theta, but I have here gamma xy divided by 2 sine of 2 theta. And then I don't need to write epsilon y prime because, as I discussed in class, this equation actually covers that too, because I just need to add 90 to theta, and then this is going to give me epsilon y prime, right? And gamma x prime y prime shear strain along the new orientation is going to be this. Sine of 2 theta plus gamma cosine of 2 theta. All right? So these are going to be my equations. Basically, knowing epsilon x, epsilon y, and gamma xy and the theta, you guys can find then for the new coordinate, the normal strains epsilon x prime, epsilon y prime, and also gamma x prime, y prime. So this equation also is similar to what we had for stresses, but if you remember for stress, we had here divided by 2, and here we had tau xy. So the equations are definitely similar, but with a small difference. All right, so if you want to, you can use these two formulas to transform your strains to new coordinate, to new orientation, right? Just similar to what we did for stress. You can also use Mohr circle for strain transformation as well. So, but we have to make one adjustment because usually I saw that the equations are slightly different. So that adjustment is very easy. So let me say Mohr's circle for plane strain. So how that works is this way. Similar to a stress, I'm gonna have my x-axis showing epsilon x and epsilon y, normal strain. Here for stress we have shear stress, tau xy. But here we have to put gamma xy divided by 2. Counterpart of tau xy is gamma xy, but you have to divide it by 2 in order to use the Mohr circle. And if it is counterclockwise, if you remember I said on Mohr circle is going to be negative, and it is clockwise, it's going to appear positive in your, in this coordinate for your Mohr circle. All right. So as I said, this approach I'm showing is for plane strain condition. So these two guys are 0, these 3 guys, okay? So if you know your epsilon x, your strains for a given coordinate, epsilon y, and then gamma xy divided by 2, gamma xy, you have to divide it by 2 and then find it, locate that on this coordinate system. Okay, so let me draw my element here so that I can explain it. Guys. All right, so you have here epsilon y, epsilon x, and then this one is gamma xy. This is a positive thing that I consider here. But when it goes on Mohr circle, you see, although this gamma xy is going counterclockwise about a point inside, so it's gonna be with this setting, it's gonna be negative. So I'm gonna have epsilon x, and gamma xy is counterclockwise, so it's gonna be negative. If I make it opposite, then I want to make it opposite to be consistent with my notes that I'm going to post for you guys on Blackboard. So if I have it in this direction, as you see, as this setting, then this gamma xy is now clockwise is positive. So that axis x is going to appear is going to be represented by just a point on this system, on this coordinate system. So this is going to be my axis x. And this axis x, the coordinate is epsilon x and gamma xy divided by 2. This one is positive, right? And epsilon y, I have considered that one positive. Let's say that one is smaller. So it's going to be here. For that axis y, my normal strain is epsilon y, and then my shear strain is gamma xy divided by 2, but this time negative, right? So if I connect these two guys to each other, similar to Morse circle for stress, where this line intersects my x-axis is going to be the center of my Morse circle, and then I can build my Morse circle. Okay, so it's not going to be easy to fit a circle here, so I'm trying to do it like gradually. Okay. All right, so this is going to be my Morse circle, right? All right, so similar to Morse circle for stress. Center of the attack, this circle is going to be located at this point, right? This is going to be coordinate of this point. And it's going to be located on x-axis similar to stress. What else? I can also find my R similarly by this equation. This is going to be a diameter of your circle, and radius is going to be 1/2 of this distance between these 2 points, right? So you can write it this way. Distance, 1/2 of the distance between those two guys. So what is the distance? X coordinate of this point is epsilon x. For this one is epsilon y. I have to subtract that. Squared plus x coordinate of y coordinate of is gamma xy divided by 2. This one is gamma xy divided by 2, but it's negative. So negative gamma xy divided by 2 squared. So I get this 1/2 of, okay, I'm going to get, take this 2 inside. If it goes inside, it's going to get squared. And then it will be 4, right? 1/4. And then that 1/4 when goes inside this parenthesis, I'm going to have this epsilon x minus epsilon y divided by 2 squared plus these two guys, gamma xy will be added, divided by 2 will be added to gamma xy divided by 2 again. So I'm going to have gamma xy. And then that 1, 2, 1/2, when it goes inside, it becomes 1/4. That 1/4 goes here. And it's gonna, so here I'm gonna have 1/4 of gamma xy squared. Then I take that 1/4 inside. I'm gonna have actually again gamma xy divided by 2 squared. So this is my R, right? This is my R, my radius of my Morse circle for strain. All right, so I have this. Now, again, similar to stresses, I have this point is going to be what? Your principal strain, the first one. So your maximum normal strain is this value. Okay, so on this one, I'm going to call it epsilon 2p, second principal strain. So no matter what orientation I consider, whatever angle I rotate this element or orientation I consider, my normal strains will never exceed this value, epsilon 1p. This tells me, this Morse circle tells me that. So no matter what this diameter, what orientation it's rotating, right? My normal strain, which is always obtained by projecting this point, my x, this denotes your x-axis. If you project it on this is going to give me my normal strain, right? Representing that x orientation. No matter what orientation this is, you guys see that cannot go beyond 1 epsilon 1p. So that's our we call it principal strain. So epsilon 1p and epsilon 2p, you can obtain them simply by this. C coordinate of the center plus and minus r. So in terms of my strains, I can write it this way. All right, so it's going to be center, coordinate of the center is going to be 1/2 of those normal strains plus and minus my r, which I obtained here. to be epsilon x, epsilon y divided by 2, and gamma x, y divided by 2. All right, so these are my principal strains. And, okay, the question is, what would be your maximum shear strain that can happen? Obviously, in this circle, you guys see that when I am here, this will be your R is gonna be your maximum, right? Your maximum happens at R. But note that gamma xy divided by 2 is maximum there. So gamma max divided by 2 is gonna be equal to R. So gamma max is actually 2 times of R. Make sense? So I have this R here. So 2 times of that is going to give me my maximum gamma, right? My maximum gamma, your maximum shear strain. All right? Okay, so I don't write it here. You'll have it in my, when I post my notes, you will see that gamma max is 2 times of R. Okay, let me write it here. Gamma max is 2 times of R. All right. So what else I can learn from Moore circle, guys? To reach to first the principal axis, I have to rotate in this direction, right? And you guys remember that stress transformation or strain transformation equations, we had 2 theta. So when we plot those stress or strain transformation equations, use this graphical approach, which we call it Moore circle, angles are doubled. So this is the angle that I need to rotate my original orientation to get to my first principal axis, right? So what is this angle? This angle is basically, you can go arc tangent. So if I go tangent of 2 theta, P equals, what is this distance? This is basically gamma xy divided by 2, right? So gamma xy divided by 2. And what is this distance? This distance is basically, this is distance from here to here is epsilon x. From, if I project it here, from here to here is epsilon y. So if I subtract epsilon y from epsilon x which is here, I'm going to get this distance, right? And then if I divide it by 2, I'm going to get this. So that distance is going to be epsilon x minus epsilon y divided by 2. Then those 2's can cancel. So to obtain that theta, tangent of 2 theta p equals what? Gamma xy divided by epsilon x minus epsilon y. All right, so this is how you can find the angle. All right, if you could find it here by taking derivative of this equation in terms of theta, setting that equal to 0, you are going to get your max and mean. So the theta at which you get your strain maximized. This is very similar to what we had for stress too. All right. So, but using Moore circle is like more clear to understand that concept. All right. All right. So I'm gonna do problems for you on this using a strain next class. By the way, I have a video also that I've posted about using Moore circle for strains. It is posted on Blackboard, and it's I think a problem from chapter 7. You can watch that too. But next class I'm gonna do a strain gauge. I'm sorry, Moore circle for strains. We need to practice this more. I have posted a few videos on transformation of stress using Moore circle. Uh, uh, they are all on Blackboard. I highly recommend you guys to watch them. Okay. Next lab. In your lab, you guys are gonna do combined testing, combined loading testing, and you are gonna use Rosette, strain Rosette. And for to give you some like heads up on that, I would like to talk about strain rosettes right now. All right, so strain rosettes are basically, you guys have used the strain gauges. You know what that is. Strain gauge is gonna give us strain in one direction, right? And if I want to find a strain in this direction, I put one gauge on that direction and it gives me a strain in that direction. But strain rosettes are basically rosettes is basically free. Let me show it. It's like if I consider coordinate system like this, strain rosettes are 3 strain gauges that are packed into one sensor, one piece. It's like a one piece you can buy from market. So, and they come with different configuration. Sometimes they come like in this form. You can see them in like one of them like this, the other one is like that, and the other one is like in the middle, like 45 degree. You can see them in like this, in like triangular shape, or other orientations. Okay, so in general, you have 3 strain gauges that are not along each other. So each of them, are actually measuring your strain for different directions. So if I call this angle theta 1, theta 2, and theta 3, they are measuring strains. Let's say if I call this one epsilon 1, epsilon 2, and epsilon 3, they are measuring your strain in 3 different directions, linear strains. So why we do this? Because I'm going to show you guys that by doing this, if you make these strain gauge very small and you attach it to a point on your specimen, knowing normal strains in 3 directions is going to help us or let us to find our epsilon. It's going to enable us to find the strains in normal strain in x direction and in y direction, normal strain, and also it's going to give us gamma xy. Gamma xy is the shear strain. Gamma is not something we can measure easily, but the rosettes, they are just with 3 linear strain gauges, 3 normal strains. We can indirectly find gamma xy. I'm going to show you that. I'm going to show you how we could do this. Okay. I just showed you that if I have my strain along epsilon x and epsilon y, and if I have gamma xy, I showed you that the strain transformation equation epsilon 1 can be obtained by this equation. Epsilon x, epsilon y divided by 2 plus epsilon x minus epsilon y divided by 2 cosine of 2 theta plus gamma xy divided by 2 sine of 2 theta. And this, for my case, if I'm interested in epsilon 1, normal strain along that line, basically for theta, I put theta 1, right? So knowing epsilon x, epsilon y, I'm pretending that I know them. But when you go to lab, you put a strain rosette, what the rosette is going to do is it's going to give you your epsilon 1, epsilon 2, and epsilon 3. You're going to have 3 readings. But what I'm interested in the problem is my epsilon strain in x and y direction, which are, let's say, my orientation that I'm interested in. Right? Okay. So once we have in this equation, what is given? When you go to lab, you measure epsilon 1, and epsilon x, epsilon y, and gamma x are your unknowns. And theta 1 is something I know, because when you look at the rosette, you will see what angle your first strain gauge makes with your x-axis, okay? So I can rewrite this equation again, rewrite that for my second gauge, right? That equation is valid for that guy too. And then for epsilon 3, theta 3, and sine of 2 theta 3. So guys, see what I have now. I was looking for, my objective was to find epsilon x, epsilon y, and also gamma xy. Using rosette will enable us to find gamma xy, which is something not easy to measure. If I was just only interested in epsilon x and epsilon y, I could use a rosette. You know, there are actually gauges you can find in market that they have 2 strain gauges, one in x direction and one in y direction. Then you put it on the specimen and you read epsilon x and epsilon y directly. But if you need the gamma xy, you are gonna need to have the third one too. Because look at this equation. If I have 3 of them, right, measured, on the left side you have those numbers. Those are given nouns. Those are nouns. And then on the right side, epsilon x, epsilon y, and gamma xy is something I'm looking for. And theta 1, theta 2, theta 3 are the angles I know, right? Because I know the setup configuration of my angles, my gauges. All right, 3 equations, 3 unknowns, right? So you can find epsilon x from these 3 equations, epsilon x, epsilon y, and gamma xy, right? And this is it. And once I have epsilon x, epsilon y, epsilon gamma xy, for any other direction that you may be interested, you can find your strength. And more importantly, by knowing that, you can build your Mohr circle, and then you find your principal strength, right? You can find your maximum strength, maximum normal strain, and maximum shear strain, right? And then knowing the strains, epsilon x, epsilon y, gamma xy, you guys can also find your, you can find your principal strains, and then you can find your principal stresses using those two, which is most of the time our objective. We are interested in finding our principal stresses, right? Okay, so this is how Rosette works, and you guys are gonna use that next week in our lab.